Hey, welcome to the fourth week of this lecture series on science and religion. This week, we are looking at our hope for scientific objectivity. And with a warning of spoilers, we may find ourselves being disappointed. But here we go. What happens to objectivity in science? So, to remind you of where we've got to from previous videos. Okay, so this is what science had hoped to be. We wanted to be looking for truth, and we wanted to be looking for universal objective truth, and we wanted to be able to find it via the scientific method. And we said that the beauty of this is that it was wonderfully interconnected, and it was all integrated. There were no bits hanging off the side that were separate, but it was all part of a whole. Though the problem that brings us is to say that if one bit of this starts to unravel, then the entire grand vision is in peril. So in the last video, we looked at the scientific method, first with Bacon, then with Popper. Now there are other scientific methods out there, but we took these as two examples, not least to show that they're not the same. And a failure to have a single scientific method and those two different scientific methods to arrive at different conclusions about what scientists should be doing and what constitutes good science starts to cause us concerns. Now, the first thing that Popper noticed is Popper's scientific method doesn't let us have certainty. And then as we started to even unpick Popper's scientific method, as we moved on to underdeterminism, what we realized is that we start to lose a handle on demonstrability, that two people with the same evidence in front of them, one might consider you have demonstrated something, while the other might say, actually, you haven't. And that indicated to us that we were starting to lose a grip on objectivity. If two sensible people faced with the same information do not have to come to the same conclusion, then we seem to have a problem. And so where we left it in the last video was with the words of Imre Lakatos, who said, few philosophers or scientists still think that scientific knowledge is or can be proven knowledge. But few realize that with this, the whole classical structure of intellectual values falls in ruins and has to be replaced. Now, that's what our whole intellectual structure looks like. And we'd hoped maybe we could stop the rot. Maybe we could, it's unraveling this far, but maybe it stops there. Maybe we don't have to lose everything. And Lakatos says, well, we might well expect that we do lose everything. So today, one piece of the unraveling puzzle at a time, we're going to look at objectivity. So Popper told us that we cannot demonstrate things to be right. We cannot, Bacon wanted to verify science, and Popper said you cannot verify science. Now, Quine came with underdetermination and said the problem of underdetermination is that you cannot falsify science. You cannot demonstrate that your scientific theory in its basic core ideas is wrong, because there are too many other things that you might have got wrong, which are entirely incidental to the core ideas of your theory. So faced with this, what do we do with science? Because we either give up and go home and say we're not doing science anymore. But many of you may have noticed from the presence, for example, of Faculty of Science here at the university, this isn't the solution that people take. So we say, well, what do we do? And we come up with other things that science that indicates that we might be onto something. We say these are heuristics. They're not rigorous, definite, logical cast iron things. But we say that science must be, or science should be, or we would expect science to be explanatory or predictive or unifying. And the presence of or in that statement is interesting. We're going to come back to that in a minute. And these are not the only things that people think science should be. Some people think it should be elegant. Some people think it should be simple. the fact that we now have different ideas as to what it should be, whether it should be explanatory or elegant, again, is going to be a flag that we're going to have to return. But we start to see already as we search around for these heuristics that objectivity is slipping away from us. So, but let's consider what these heuristics do in science, and we're going to consider it. We're going to leave evolution to one side for this video. I'm a physicist, I'm a quantum physicist, so we're going to consider it in terms of quantum mechanics, and specifically in terms of the Bohr model, which was one of the very early theories that started to move in the direction of quantum mechanics. So let's consider science must be explanatory. Now let's look at explanation within the Bohr model. So within classical physics, you started off up to the end of the 19th century, physicists had most of physics pretty much sussed. Basically, the things that they couldn't do, they couldn't explain light bulbs and so old-fashioned tungsten light bulbs, and they couldn't explain sodium street lamps, right? Light bulbs are the real problem, right? Couldn't do tungsten light bulbs, and they couldn't do sodium street lamps. But everything else they had sussed. Once they could solve these two, they were good. Now, if you have, we're going to go for a bit of physics here, so strap in, hopefully we can follow through. Okay, if you have a charge being accelerated in an electric field, that accelerating charge radiates energy. So if I have a proton at the middle of my nucleus and I have an electron going round it, well, my proton sets up an electric field, and my electron going round it is a charge. It's got a negative charge on it, and the fact that it's going in a circle, not a straight line, means it's being accelerated. So this means that an electron going around a proton is an accelerated charge, which means it should radiate energy. And as it radiates energy, it should lose energy. And as it should lose energy, it doesn't stay going around in a circle like this. It spirals into the nucleus. So within classical mechanics, we have this very simple situation that says if an electron is orbiting the nucleus, it should spiral into the nucleus in very short order. And you can test this experimentally. What you do is you wait for a second and you see if every single atom in the entire universe collapses. So we can do this experiment now. Right. And for those of you who haven't collapsed, we know that this theory is clearly wrong. And this is a problem. So we know it's wrong. We don't know what to replace it with, but we know that clearly this isn't happening. Now, another problem they had, and this is where we come to sodium street lamps, is that it says if you have a gas and you shine white light through it, so light that contains all the colors of the spectrum, most of those colors go through. But some of those colors, very specific colors, get absorbed. And it wasn't obvious why. Now, if you take the same gas and you stop shining light and you turn a current on it and you run a current through it, well, it starts to emit light. And it emits light at exactly the same colors as it would have absorbed light if we were shining light through it. And it wasn't clear why that should happen either. And these absorption lines, they're very distinct. They come in very specific places, which are characteristic of a given atom. So a sodium street lamp has a very characteristic yellow color. Neon lamps have very characteristic colors. For those of you who do chemistry, the flame test that you do, you look at the color that comes off that and you know exactly what chemical you have. And it wasn't clear why you should have these very clearly defined, very characteristic, very distinct lines. So these are the problems that classical physics was facing. We can do planets, we can do tables, we can do rocks falling off the Leaning Tower of Pisa, right? But what we can't do is we can't do these questions here. And people working on classical mechanics had worked for a long time and they couldn't work out the answers. So along came Bohr with 3 postulates of quantum mechanics. And here's what he said. Here were his answers. First, postulate 1 is that the electrons orbit the nucleus without falling in. Now, if you come to someone and you say, why doesn't the electron fall in? And they say, the electron doesn't fall in, you might feel that you haven't necessarily been given an explanation. being told that the thing that you want to know why it happens, by most standards isn't an explanation. But here we go. Let's see if we do better for the other things. Okay. Why do you get narrow emission and absorption lines? Electrons move between stable states by emitting or absorbing narrow line width radiation. So I have my electron going around here, and then I go from this state to this state, and it jumps between the two, and that's what it does. Well, okay, there's more words in that explanation. Is this an explanation? Now, instead of asking why we have narrow emission and absorption lines, we say, well, why does the electron move between stable states? Right? I mean, we've moved the conversation, but it's not obvious that we've moved the conversation forward. We've just kind of moved it sideways somewhere. And one can say, yes, but now we have explanations because we can explain it in terms of wave functions. But you say, well, that's later. Did Bohr, at the time he was writing, know that these explanations would come later, or was this just a hope, a faith in the future progress of science? And if so, does explanatory power permit faith in the future progress of science, and what does that do for science? So even if we say we have an explanation now based on this, and this was the first step towards that explanation, that's not the same as saying this was at the time explanatory. And I should also point out, when I was originally writing the notes for this, David looked at the explanation I gave and said, that is not an explanation, right? To talk about wave functions, I mean, what's a wave function? And so here we have another problem that says something that I consider to be an explanation. It's like, well, obviously, okay, if the wave function is over here, then it's going to do this. That's an explanation to me because the wave function says so. Whereas David says that is not an explanation. We're faced with more or less the same information. What's different? Well, I come with a different set of knowledge and background and connections and assumptions and things where I'm just prepared to say, yeah, fine, I accept that. And maybe David's more skeptical or less well trained in quantum mechanics. And so it's not an explanation for him. And so there's nothing objective that says this set of information here has to be accepted by everyone as an explanation. There is something subjective, because essentially an explanation is whatever needs to be said in order to get you to go, oh yeah, that makes sense. And it's common, you will surely have found this in your classes, that you can have two students go to the lecturer after the lecture and say, I didn't understand this bit. And the lecturer says, well, this and this and this and this. And one student says, oh, right, okay, that makes sense. And off they go. And the other student says, no, it doesn't. So even if science must be explanatory, we find that explanations are subjective as to what counts as an explanation. And even given that, we find that science here isn't being explanatory except for calling on a future hope of an explanation to come. Okay, well, maybe point 3 is going to be better. Okay, explanation 3, or answer 3, the energy levels of the electron are discrete. Well, again, the absorption lines are discrete because the energy levels are discrete. Well, have we moved anything forward? It doesn't seem, by many understandings of what we want explanation to mean, that quantum mechanics was explanatory. Now, some people at the time argued that this means that quantum mechanics was not science. Many of the founders of quantum mechanics argued that. Now we tend to look at it and say, well, science doesn't need to be explanatory. Okay, science needs to be predictive. How about this? Well, this is pretty simple, all right, because you can look at Bohr and his postulates, which he published in 1913, and they predicted the energy states of the hydrogen atom, which had been measured by Lyman in 1906. Now, as far as predictions go, that's not a very good prediction. It came some number of years too late. So here we say, well, okay, maybe Bohr didn't know about it, right? It's a prediction as long as he hadn't kept up with the literature. So now we find that scientists who don't understand the field around them, don't keep up with the research in the field, can do science that wouldn't be science if they'd actually been reading the papers in the literature, because people that know what's going on, it would be a post-diction or just what. That seems strange, that you can do science by not knowing what's happening around you. So if Bohr did know what was going on, it wasn't a prediction. And if he didn't know what was going on, well, this does something strange as well. So there were other things that he did predict. And for what it's worth, all of the things that he did predict, he predicted wrong. Not very wrong. He was fantastically close. When he said, okay, this is where these spectral lines in the hydrogen atom should be. He was really, really, really close and ever so slightly wrong. And so we say, okay, was it? And he knew it was ever so slightly wrong because it has been measured already. So here we say, okay, well, this is a prediction, which means that it was falsified from the get-go, or we say that we'll give him, you know, award marks for effort because he was almost right. At what point do we fudge it and say, yes, this is kind of a prediction or a close enough prediction, or let's... Anyway, prediction within science is not as simple and obvious and clear cut as one might think it would be nice for it to be. So let's move on to science should be unifying. Okay, and this one for quantum mechanics, this is simple, right? Okay, quantum mechanics is, bar none, the best scientific theory we have when it comes to just testing it and showing it works, right? If you get a prediction from quantum mechanics, right, you can test it and you can check it, and, you know, you can stick 1 part in a million on this and it's right as far as we can test it. Quantum mechanics, you know, when you want to describe an atom, when you want to say what color should this be, quantum mechanics as we currently have it is insanely good. It's really, really good. It's hard to stress that strongly enough. And yet, here's what Bohr's model could describe. He could describe hydrogen. Now, if you remember back to the beginning of this video, I said that classical mechanics could describe planets and falling rocks and tables. It could describe cars. It could describe, well, okay, not... yeah, okay, 1900s, it could describe cars. Newton couldn't, but hey. You know, it could describe pretty much everything except for light bulbs. Now, Bohr could describe the hydrogen atom badly, and that was it. Okay, so he could not describe... So hydrogen is 1 proton and 1 electron. If you added another proton and another electron, so you had helium, he couldn't do it. If you said, okay, we'll just add another proton, but no more electrons, right? We've just added 1 more particle. So we've got positively ionized helium. This is about as simple as you can get. 2 protons and an electron. Can't describe it. Working your way up, lithium couldn't describe any of the larger elements. If you said, okay, well, we can do hydrogen, maybe we can do 2 hydrogen atoms. Okay, hydrogen molecule, proton, pair of electrons around the outside. Can we describe that? No. Okay, well, throw another electron away. We've got 2 protons and they're both now in positively charged hydrogen molecule. Can we describe that? No, we can't. Can we describe classical mechanics? No. Can we describe electromagnetism? No. Can we describe planets and falling rocks? No. We can't describe anything that classical mechanics can describe. Now, that is, by almost any reckoning, not a unifying theory. We can describe nothing that our previous theory could describe, and only a very small fraction of what our previous theory couldn't describe. Science, if Bohr's model was scientific, does not need to be unifying. Okay, so what happened? How did quantum mechanics ever get off the ground if this was the situation we were facing? Okay, so here is the situation that scientists were facing at the start of the 20th century. Classical mechanics had some problems, not very major problems, just minor problems. If you didn't care about streetlights and light bulbs, you could get a very, very long way without caring about the problems of classical mechanics. But for these few problems, it had spent a lot of effort from a lot of really, really smart people trying to fix them, and they'd tried lots of different ways to do it, and they'd failed, and they were running out of ideas for how to fix it. Now, quantum mechanics was exactly the opposite, in as much as it had problems. It had lots of problems. It had big fundamental problems. It had problems that just jumped out at you and smacked you in the face and said, I am a huge big problem, not least because I undermine your very notion of reality and what it means to do an experiment and anything, what any of this means. I mean, it had big problems. You couldn't come near quantum mechanics and not be aware of them. But it wasn't yet running out of ideas for fixing them. Now, the main reason it wasn't yet running out of ideas for fixing them is because no one had spent any time trying to fix them. It was a brand new theory. And you go, well, okay, maybe we can fix it like this, or like this, or like this, or like this. And probably most of those wouldn't work, but we didn't know that they wouldn't work because we'd not yet tried them. No one had spent any time, certainly not really, really smart people, for their entire careers. So we hadn't run out of ideas for fixing them. So there was lots of research that could be done. So for quantum mechanics, on the one hand, you say, okay, well, you know, if you're being uncharitable, you say this has been falsified from the moment you propose the theory. And on the other hand, you say, well, but we have lots of new ideas for how we can fix it, avenues for research and things that we can look at. And the difference between being falsified and having an avenue for research is, in one case, you stop giving someone money, and in the other case, you give them more money. And so we say, fine, let's go for this. Now, the question we now face is, you have to weigh up, because we can't falsify either of these, and we can't verify either of these because of underdetermination. So now we're looking at, do I go for a theory which is really, really useful and helps me to build cars and you know, later aeroplanes and rockets and all sorts, right? Do I use this theory, but where I'm running out of ideas, or do I use this theory which is shot through with problems but has lots of opportunities? And how do I weigh one of those against the other?